The second presentation is studying the relationship between BKT and assessment error. And Francesca?
Yes.
Francesca is going to begin and take it away.
Okay, good afternoon. Thanks for attending. I will be presenting studying the relationship between BKT fitting error and the skill difficulty index, say skill, say knowledge component, whatever looks best. Okay, as my colleagues said before, BKT is a student modeling algorithm which is used to infer students' knowledge given a set of questions which are given. You can get it right or you can get it wrong, and according to your answers and a certain group of parameters, you are assessed the probability that you have already mastered that skill. Okay, usually a separate BKT model is fit for each skill, for each knowledge component. Usually only the first attempt at each question is taken for each student, and usually one set of parameters is used for a whole group of students. Okay, those are the known formulas that allow you to calculate BKT and the meaning of each parameter. Okay. In previous research, actually last year at TDM, we presented and we found that not the super high correlation between the fitting error and the skill difficulty index was found, 0.978. I was wondering if anyone could tell me why I was wrong. No one managed, so I continued until someone please tell me to stop or I'll do something crazy. Given that, we brought the three questions. Well, does the relationship hold on different data sets? It's meaningful. It might be meaningful. We'll pick on different data sets and to see if this continues. Do we observe, and this was a question we created, we find out after doing part of the research, is there any sort of central limit theorem or sample size effect in this correlation between BKT and the fitting just the fitting error, BKT's fitting error and the skill difficulty, sorry. And can we say something about identifiability problems and local minima? Because the way we estimate the parameters let us easily look at these things. Okay, so to do this research, we use four data sets. The first one was already used in the research last year, and we had the other three. We had them because they were different enough in terms of number of skills, in terms of ages at which students were answering the questions, in barely everything, and number of records in the data set. The number between brackets in the skills are the skills that we actually used for our model, because they are those who are tagged in with at least 4 different questions, because if you have less than 4 different questions in a skill, it's sort of difficult to see if BKT is working properly. Okay. To use this, we use an old friend known as BKT brute force, which is a terribly long algorithm to estimate the parameters, but the nice thing is that you have a perfect mapping of all the answer, the response field. Okay, that's why we use it. Then we will use for L0 and T, we'll use a step ranging from 0.05 to 0.95, which is a 0.1 step. 0.05 step for G and S, and we'll use values ranging from 0.05 to 0.30 in order to avoid degeneracy in the model. We are not using a very small step because we don't want a super precise estimate of the parameters. We just want to see how the response field looks like. Okay, so 3,600 different RSS values have been obtained per skill. And instead of using 3 RSS, we'll use RMSE because we will be able to compare the different scores for the different models. And it's a normalized version, which, depending on how it looks, pretty normally distributed, and it ranges from 0 to 1, although if it's a binomial problem, it should be from 0 to 0.5, which will look as a problem later on. Okay, difficulty index is nothing more than 1 minus the error rate. Difficulty index works perfect for confusing the audience, because the higher the difficulty index, the easier the question is. But that's how psychometrics define this somewhere. Oh yeah, sorry. And we have used the difficulty index in terms of one difficulty index for the set of skills. For knowledge components. So we gathered all the answers for all those questions with that knowledge component, and then we calculated the difficulty index. So, well, maybe we could improve that, but that's the best we could think of. Okay, to study the effect of the data set, we will of the sample size in the data set, we will take random samples from 100,000 data to 1 million points. We'll use only the MOOC, the data set from OLI MOOC psychology. And in this case, yes, we will include all skills in the analysis, because if we impose the condition for more than 4 questions, then well, it would be hard to see anything, because we are pushing it too hard. Okay, so in terms of results, we draw some contour plots using the errors from the BKT BF estimates. I'm just showing one of the contour plots, but we have them all, and they don't present any local minima problems, but we indeed see very large optimal areas, which might be the source for the identifiability problem, rather than, as it was said somewhere, problems in the optimization process. Okay, we also see, and that's, we haven't dig much there, that some of the contour plots have some very independent effects or very flat slopes. We have to work on there more, but this looks interesting. Okay. Well, in this plot here, we see that the parabolic effect holds on very well in different, don't know the words in English well. We have the circle is for MOOC psychology, the triangle for algebra, physics, which is a very small data set, is the one that seems to be much off the line. And but at the same time it was the smallest data set, so that's, I mean, seeing this what brought us the need of studying the sample size effect in this data set. Okay, see that I mean, the difficulty index fits very well, especially at it fits very well. And related to what I was saying before about RMSE, it's very close to 0.5. So that's part of what concerns us the most. That when difficulty index means something, like the skill is pretty difficult, so that around 50% of people will make it. At that point, BKT makes a mistake. I mean, the RMSE for BKT is 0.5. So that's troubling.
Just a quick clarification.
Yep.
Each point down here is a kid or a skill?
Each point here is a skill. Is the BKT BF RMSE for the best RMSE it can make. Yeah. Thank you. That's okay. And then to see the eyebrow depilation process that the sample size effect has, we have drawn here the effect. The top left chart is for 100,000 data points, for 100,000 data points. For the top right, 700,000, and the full data set. And we see that, yeah, there is. I mean, that's not surprising. We were expecting this. But it gives an idea that maybe if you're not working with a very big data set, you might not see this. If you have 34 students and 1,500 points, you will not see this, because you need 1 million points to see it. Okay, and the discussion that was short. The parabolic relationship exists, keeps on in 3 new data sets, which are different, pointing at different students, different sizes, different, in which we could show in PSLC as different as we could try to work with. Okay? No local minima problems have been found, but there are very large optimal areas. But still, we will have to keep on working there to see if this is general or just the different skills towards I took a look that we observe that. The parabolic behavior of BKT depends that BKT performance highly depends on difficulty index of the skill. That's the finding. If the error is so much correlated to the, if you could if you can fit a parabolic model with the difficulty index, that's what it's telling you. So if it works, your skill is either too easy or too difficult. Otherwise, the RMSE is very big. In EDM, I asked I don't know to a question I answered I don't know to a question I was asked. After thinking it for a little bit, it's just a hypothesis. But what we could think of this parabolic effect is that it's an interaction of mastery and S for the first part, so the difficulty index itself, and the probability of not knowing, and the G parameter for the 1 minus the difficulty index part of the parabolic thing. At last, there is an important sample effect in the quality of the fit between RMSE and difficulty index, which has these implications that you might not see this if you are working with a small data set. And future research lines should focus on individualization. I mean, the part that we take the most is that if you use just one model for all students, some of the parameters seem to be not fitting well at the skill level, and they should be some sort of student skill level in terms of, so that it works properly, okay? And we'd like as well to see how the parameters are related to, well, the different findings that we have been finding. And that's it. Thank you. It looks really interesting. Before making mistakes, I'll say I don't know, so that I can do more research for next year. And I guess this will continue happening, but I'm still, well, maybe it's just I'm not, I can see it better than this, but that much of an effect, isn't it really, isn't it also saying that there is some individualization needed in the model fitting? Because if you're using all students,
forget this, because this is loaded. Imagine basic probability. You take coins that are loaded. See, always heads to always tails, normal coin on the middle. Okay?
Sure.
The prediction for every coin is exactly the probability. You know what it is. It's written on the coin.
Okay.
Then you flip the coins 1,000 times, and then you construct your measure of error, which is whether you got heads minus the probability. You do your plot, you get a parabola exactly the same way. So it's nothing to do with the models. It has to do with the fact that it's very hard with a measure of error, which is a binary outcome minus a probability. By definition, by construct, you're going to get a very large distinction at 50% and at the tails. Sorry.
Yeah, I agree. I totally agree. But still, that's the okay.
This is a good talk, and I'm excited to see this. And I recognize that you started your talk kind of saying, you know, hey, am I an idiot? What, you know, should this be happening? And just so you know, I've been in this area a long time. I don't know the answer to this, so you got me stumped for the moment. I think he's onto something there, but there may be something also important that we're not paying attention to. But can I ask a clarification question? How do we deal with the definition of the difficulty index? Is that the average percent correct across all the students that did all the items of a given skill? Or is it just like the first item correctness? Or are you using something like the IDM model that actually is giving you difficulty like in a latent sort of way? What is the difficulty index?
It's in BKT estimation conditions. It's just the first attempt.
Okay.
Just for the
So
first
just
attempt.
the average
Yep.
correctness on the first item. Okay.
For answers of a given skill.
Any other questions? Going once? No? Thank you very much. Okay. All right, for our last session last paper of this session, we have modeling common misconceptions in learning process data. And this is, I will note, also a best paper nomination. So, take it away.
Thank you. My name is Ran Liu, and I'm from Carnegie Mellon University. And just a little caveat, this presentation is in the Bayesian modeling session, but it has almost nothing to do with Bayesian modeling. So sorry to disappoint any of you who came here for that reason. But I hope you'll still find the talk interesting and perhaps even help me brainstorm some ways that our approach could be incorporated into models like BKT. All right, so as the use of educational technology becomes more and more ubiquitous, the usage data that's logged by such technologies can provide us with a lot of rich data for assessing and understanding students' skills and concepts and mental models and learning trajectories. We can think of these aspects of human intelligence collectively as a knowledge base whose elements are knowledge components. And so Kantiger, Corbett, and Perfetti defined a knowledge component as an acquired unit of cognitive function or structure that can be inferred from performance and relevant tasks. Modeling educational data typically requires something like a knowledge component model, which involves the mapping of these actual knowledge components to tasks or problem steps. This knowledge to task mapping provides a way to convert basically a symbolic cognitive model into a form that can be used by statistical models to make predictions about student performance on these tasks or problem steps. So I'm just going to give you guys a simplified example of something that you might see in a KC model. So the domain that I'm actually going to be talking about today is fraction arithmetic, so the example is from that domain. So these columns you can see are potentially relevant knowledge components to doing fraction arithmetic. And in this first problem step, the student has to multiply 1/2 times 3/4, and so the knowledge component for the procedure for multiplying fractions might get tagged. Similarly, if a student has to add two fractions with different denominators, they have to apply the knowledge component that supports knowing the procedure for that. And in addition, sometimes you'll see that there are additional difficulty factors present. And so there can be multiple knowledge components tagged for a single problem step. In this particular case, in order to execute the correct procedure for adding these fractions, the student has to know how to find the least common denominator and also has to know how to find equivalent fractions once they've determined that least common denominator. So when you couch this kind of KC model within a statistical model, or basically like a mathematical abstraction of the relationship between various features of the learning environment and some kind of observable outcome of learning, you can start to make inferences about student knowledge based on observable behaviors. So for example, if the student gets the multiplication problem correct, then typically a student model will then update its estimate of how much that student knows the procedure for multiplying fractions. And similarly, it would update, well, at least in additive models, it would update its representation of all the knowledge components tagged for this fraction addition problem to improve the likelihood that the student knows those. All right, and if the student gets the multiplication problem wrong, the model typically will decrease the estimate of the student's knowledge of the fraction multiplication procedure in typical models. So the vast majority of educational data mining work has focused on estimating students' positive knowledge components. That is, knowledge components that really can only help performance on relevant tasks or problem steps. So when students make errors, though, as seen in the previous example I just showed you, student models will typically respond by lowering the likelihood that the student has the relevant positive knowledge component. So it is true that sometimes errors reflect a simple lack of knowledge about how to do that kind of problem step. But oftentimes, students make errors that reflect a thoughtful but incorrect strategy. For the purposes of this talk, I'm going to call this sort of class of thoughtful but incorrect concepts or strategies or procedures as misconceptions. So I've talked to some people already about this work, and I guess the term misconception has been used to refer to something more specifically conceptually grounded. So I'm just going to ask you to forgive me for this terminology, and maybe if you have any suggestions about a broader term I could use to capture, you know, like misconceptions, misprocedures, all of those kinds of things. So the goal of this work that I'm about to present is to extend KC modeling to accommodate the representation and the assessment of misconception-like KCs. Okay, so the current state of KC modeling is that any given KC can only be positively mapped to performance on a problem step. So this doesn't really allow for us to model misconceptions as KCs since they lead to negative performance on at least some problem steps. So we propose to extend KC modeling to accommodate misconception-like KCs by mapping them to problem steps on which they could apply, but to use -1 in addition to 1 and 0 coding. So misconception would get coded as a -1 or it would get coded as a 1 for problem steps in which applying it gives you the correct answer, but for the wrong reason. And it would get coded as a -1 anytime it would yield an incorrect answer. And then, just as with normal KC modeling, any problem steps on which it applies would just get coded as 0. So I'm going to present to you a case study where we applied this to a particular misconception in fraction arithmetic, and hopefully that will give everyone a more intuitive sense of how we were able to code this misconception into the data, as well as what effect it has on the model. Okay, so the misconception that we focused on in fraction arithmetic is called independent whole number strategy, and it's very commonly seen among students. I guess you could call it more of a misprocedure. But basically in this strategy, students basically just apply the operator that's in the problem to the two numerators to generate the numerator of the solution, and then they apply the same operator to the two denominators to generate the denominator of the solution. So you can see in these examples that when applied to multiplication, students will generally get the problem correct, and when applied to addition, they will generally get the problem incorrect. So this is an example of the tutoring interface that the data set came from. By the way, just a side plug, this tutor was created using cognitive tutor authoring tools, which is something created at CMU that you can really use to create any kind of educational intelligent tutoring system. And so you can see this is a very simple interface. Students get to, in this problem, input just the numerator and the denominator, and they get immediate feedback and can ask for hints and all that good stuff. And similarly, this is an example of the multiplication interface. And then here's an example of addition with two different denominators. And just to note, since you'll want to reference this in later slides, there is this little checkbox that students have to check to indicate that they recognize that in this kind of problem, they have to convert the fractions to have a common denominator before they can proceed. So once they check this checkbox, you can see these additional, sorry, it's a little bit hard to see on the screen, but these additional squares and, well, additional fraction components appear so that it gives the student a way, an intermediate way to convert the fractions first before adding them with a common denominator. Okay, so that's just an example. So this data set is available on PSLC Data Shop. Yeah, I think we uploaded the KC model there as well, so you can access that. I think you have to request permission, but it should be granted. All right, so we started off with an original KC model that was created by not only a domain expert, but also someone who's an expert in studying how students learn fractions. It's my co-author, Ronnie, created this original KC model. So I'm not going to go into every single detail, but I'll leave it up there for a couple of slides, and you can check it out. Now, the interesting part is kind of how we decided to code the misconception in. So you can imagine that all of the green circles are 1 and all of the red circles are -1. So I'm just using that scheme to show you how we coded it. So you can see here, when you add fractions with the same denominator, adding the numerators is the correct, or will generate the correct numerator answer if they're just simply applying this strategy, but adding the denominators is not right. So essentially it predicts that the student would get the numerator right but the denominator wrong. Similarly, for multiplying, they would get both the numerator and denominator correct, so both are coded as 1s. And for adding fractions with different denominators, they would not only get this checkbox wrong because they're supposed to check it before they proceed, but they would also get both the numerator and denominator wrong on their first attempts at either. And then once they've sort of progressed past that phase, there's still another opportunity because they're going to have to later add fractions with the same denominator, and they might, again, add the denominators. So there's an example there. All right. So before I show you the modeling results, I'm just going to do a quick overview of the statistical model that we used in conjunction with this misconception KC modeling approach. So we use the additive factors model. It's a logistic regression model that basically models the probability P ij that student I will get a problem J correct based on the student's baseline ability, as well as the baseline ability for all skills required on any given item, the baseline difficulty of each of those skills, or easiness, you can think of it as that, and also a learning rate for each skill. That's basically multiplied by the number of opportunities by that item that the student has had to practice that skill. So we worked within this model because there's a lot of precedent for using the additive factors model towards KC model improvement. All right, so I'm not gonna go through all of these coefficient estimates, but just to give you a sense, the additive factors model is essentially going to give us an ability estimate for each student. That's the student intercept. And in addition, for each of the normal skills in the KC model I had shown you earlier, it's going to give you a sort of easiness estimate of that skill, and it's going to give you like a learning rate estimate of that skill, and that's what the slope refers to in those. All right, so first what we did was just added simply an additional intercept for this misconception KC. And you can see that right away, so we use AIC and BIC to assess model fit. They're essentially log likelihood with penalty for adding additional parameters. And you can see that the AIC fit, so lower is better in this case. And you can see that the fit improves with the addition of just an intercept for that misconception KC. And the BIC improves as well, and it has harsher penalties for additional parameters, so that's good. And then in addition, you can see that the misconception KC, the coefficient estimate for that intercept, is quite positive and quite statistically significant, suggesting that there is, in fact, a strong presence of this estimated by the model in the data set. And just to kind of give you an intuitive sense of what happens to other KC estimates, as you add something like that misconception in, you can see that the coefficient estimate for the procedure for multiplying has actually decreased, meaning that the fact that students are probably getting some multiplication problems correct just because they're applying this strategy, maybe not because they necessarily know that that's what you're supposed to do for multiplication, will lead it to, lower the estimate for the likelihood that they know the proper procedure for multiplication when they see a multiplication problem. In addition, for something like finding the least common denominator, typically when students